Assalamu alaikum, student. Today our lecture is about Cipher and its different variants. This is our first lecture. In this lecture, we are basically design some new encryption algorithm that is basically the extension of Hill Cipher. The Hill Cipher is fundamentally based upon linear transformation, and it means the transformation is basically from set of n tuple to set of n tuple. In that case, the matrix of transformation is square matrix, and in that case, matrix has some inverse as well as determinant. Determinant is possible. But today class is about some variant of Hill Cipher. Basically, we are given two different variants of Hill Cipher. One is about how one can use rectangular matrices instead of square matrix to generalize the idea of Hill Cipher for square matrix to rectangular matrix. And then second one is how we can relate determinant permutations as, with determinant. Means to say that second case we are basically relating symmetry group with general linear group over binary field Z2. First of all, before developing the Hill cipher for rectangular matrices, we know something about some basic knowledge how one can calculate the inverse of rectangular matrix. Fundamentally, the inverse of matrix is based upon rank of a matrix and rank of a matrix, and we call it pseudo-inverse technique. So let us start with the first topic of our present lecture. This is Hill cipher based on pseudo-inverse method. These are fundamentally some definition that a rectangular matrix have to have satisfied these equation 1 to 4 in order to be to have some what you call pseudo-inverse. And how to construct the pseudo-inverse, let us take one remark in slide 3, construction of pseudo-inverse. For given matrix A that belongs from set of M cross N matrices, the pseudo-inverse, which is represented by A hash, is belong from a set of N cross N matrices, is unique. If number of say M is equivalent to N, means to say number of rows and number of columns are same. In that case, the rank of A is M and the pseudo inverse is same as the traditional inverse of a matrix. If uh, number of rows is less than number of columns, then rank of A is M, then A into A transpose is non-singular. In that case, the pseudo inverse is represented as in this expression. A hash is equal to A transpose, A into A transpose, inverse of A into A transpose. If number of equation is, say, number of rows is greater than number of columns and rank of A is N, then A into A transpose is non-singular, and in that case, the pseudo-inverse is equivalent to this expression. Let us take one example where number of equation is greater than number of column. In that case, we have to take third possibility of the remark, which is given in previous slide. If A belongs to set of the matrices of 4 plus 3, say this is a matrix whose rank is 3. In that case, the pseudoinverse is represented by this expression. We put A, all the expressions, put the values of all expression in that equation. So we will ultimately get inverse, means to say pseudo inverse of A, which is A hash 1 over 24, 2400 minus 16, 80, 4 minus 8 and 6. This will be very good if you can find out these calculation over MATLAB or Maple. That will be very good for you in order to apply this method to some digital medium. Let us take one example, Hill cipher using rectangular matrix. I write down here as a transformation from ZRN to ZRN. In that case, the M is not equivalent to M. In that case, A is of order M class N. Say then the resultant is of order m. In that case, this y1, y2 up to ym as m tuples, and these are belongs from this output set, and these are the input x1, x2 up to xn. These are belonging from zn. Are the individual values are basically the element of zr, and we call it ground set. Zr is called ground set, from where the individual element are belonging from. So this is a encryption algorithm that you have to apply a rectangular matrix with the input. You will get output m cross 1 tuple column vector, which consists of m rows and one column. In decryption, we have to get back our input, means to say plain text x1, x2, xn. It is multiplied with the inverse of this matrix. This is not just a traditional inverse. This is basically uh, pseudo-inverse is multiplied with cipher. M cross is basically M cross 1 column vector, and this is a N cross M matrix. So we have to multiply and get back our plain text. Let us consider one example. Say we take our ground set as a Z29 alphabets, means to say we have Z29 as a ground set, and we have basically 26 alphabet, and we add three more alphabet into our set in order to extend our uh, set for encryption. A set A is one we have solved in previous example, that its inverse is pseudo inverse is basically possible. For that reason we take this A. Let us consider plain text P, that is strike at noon. Strike at noon, basically blank is 26. So we put our matrix P into here. The order of matrix is 4 cross 3. So we have to place our matrix in 3 cross some, it must have 3 rows, and, and you can place over here 3 rows. It must have 3 rows. Rows in order to make it its multiplication compatible. So we place all these strike at this plain text in 3 cross 5 column matrix. This is 1 2 3 1 2 3 4 5. So to get ciphertext, we are multiply A, which is a key matrix, with P plain text, and we get matrix of it is basically 1 2 3 4 4 rows, and 1 2 3 4 5 column. So 3 is map on D, 9 is map on J, 22 is map on W, and so on. 25 is map over Z. So our ciphertext is DJ, W, so on, and G, Z. So, in order to get back our plain text, we have to apply this pseudo-inverse, which is we have find in our previous example, and convert this matrix into a mod 29. Basically, we have to remove this fraction. And basically, in Z29, there is no fraction, so we have to remove the fraction in order to use our matrix effectively and map the corresponding value to some alphabet in our set Z29. So to get plain text, P is equal to the inverse of a rectangular matrix into C, and the PA is basically uh, 3 cross 4, and this is basically uh, 4 cross 5. So ultimately we have multiplied both and mod 29, the whole the result will get back our plain text, which is strike at noon. So one thing that really makes sense in this whole uh, encryption algorithm, which is based on rectangular matrix, that this matrix is again based on linear transformation, and Hill cipher is also based on linear transformations. And linear transformation is a transformation in which lines are mapped on lines and origin is always fixed. And again, there is a thread. There is a thread for this encryption algorithm too. So we have to go for another extension of Hill cipher. Let us consider another variant of Hill cipher. The Hill cipher that is based on permutation matrix. What does means permutation matrix? In mathematics, particularly in matrix theory, a permutation matrix is a square binary matrix that has exactly one on entry of one in each row and each column and zeros elsewhere. Uh, each such matrix, say P, is represented by permutations. So let me try to define this with example. We have to understand this with the example. Let us take symmetry group S3. This is identity permutation. This is another. It has basically 6 permutation. Let us take identity. We have map identity permutation with this identity matrix, and this 1 2 is basically in the identity matrix. 1 is map on 2 and 2 is map on 1. So and secondly, to 1 is map on 2. So we place this one. So here in this case, that is 2 is map on 1. So here the 2 is map on 1. So in that case, 3 is one map on 1 and 1 is map on 3. In that case, 3 is map on 1 and 1, 1 is map on 3. That is 1 is map on 3 and 3 is map on 1. So here the identity matrix there is a 1. So 1 is map on 3 is map on 1. So in the rest case, we are doing the same. We get basically 6 matrices corresponding to 6 permutations. So this idea is utilized in while developing the Hill cipher that is based upon permutation matrix. Let us start with some encryption algorithm that is involved in the Hill cipher based upon permutation. Let us say we select permutation from any symmetry group, select matrix H, which is a basically key matrix, calculate permutation P permutation matrix corresponding to these permutations, and also calculate its inverse permutation in order to calculate H pi. The H pi is basically this equivalent to this expression, and then we have calculate Y, which is H pi times X mod, and X is basically your plain text. So ls and then h pi dash, which is equivalent to h pi. And let's send uh, pi dash h and y to Bob. On receiving end, he has to find the uh, corresponding from plain text to corresponding ciphertext. From ciphertext to plain text. In decryption, we need inverse of key matrix, then H inverse pi, which is H inverse pi, uh, pi dash, and then calculate permutation matrix P as we calculate from in previous steps of encryption. Then calculate H inverse pi, which is pi inverse H times pi, and then X is multiply to get back plain text. We have take this inverse and multiply it with ciphertext, and we get back X, which is our basically plain text. In order to understand this algorithm, let us take one example. We exemplify this with S3 symmetry group, uh, three element. So we take one permutation, that is one is map on two and two is map on one and three is map on three. We take one key matrix, say H, and then plain text is our plain text is 0 to 9. By using permutation matrix corresponding to this permutation, we have this permutation matrix and its inverse. We have obtained its inverse. So we need to calculate H pi, which is mm, P pi inverse time H into P pi. We have calculated this and we get this matrix of 3 class 3. In order to encrypt our plain text, we multiply H pi with our plain text and we get 853 as a ciphertext. Uh, Dear student, in order to get back our plain text from ciphertext y, we have to calculate h inverse pi, which is equal to pi inverse time h inverse time p pi. So we have ultimately calculated this, all these, perform these all calculations, and we get this matrix, which is perhaps need in process of decryption. So we have calculated this inverse matrix with y and get back our plain text. So again, students, we have involved uh, some matrices, and we add some more complexities to our traditional Hill cipher. And we have not only have one matrix, we have more than one matrix, as well as we have in this algorithm we introduce another structures of symmetry group. And here our basically this whole encryption algorithm not just depend upon one non-commutative group, but this is depend upon two non-commutative groups. So and moreover, the possibilities to uh, to perform to get back your key is key. We need more possibility as compared to traditional Hill cipher. In next line, we will show some geometric transformations. So why we need a fine transformation instead of Hill cipher. Let us take these two very famous transformation. These are how to relate these Hill cipher with some geometry. There are basically two types of basic geometries that are quite useful in cryptographic applications. One is linear transformation, and second one is affine transformation. The linear transformation is fundamentally required while you're developing any diffusion component, whereas affine transformation is fundamentally required whenever you want to construct a confusion component, and confusion component means to say a non-linear component. In that case, basically linear transformation is not quite useful, because in linear transformation origin is always fixed. Means to say, whenever the input is 0, the output will always be 0. But in case of affine transformation, 0 may not be map on 0. That means to say there is uh, quite possibility in linear transformation that we have a number of fixed points, but as compared to affine transformation, it has less number of fixed points. So that is why usually whenever we are building or designing any non-linear component of block cipher, we are used to have to have used the affine transformation instead of linear transformation. So there are some properties of linear transformation, like linear transformation are basically the combination of scaling, rotation, shade, and mirror. And this is one of the fundamental properties of any linear transformation from any set of n-tuple to m-tuple must satisfy this property that origin maps to origin. That is, whenever we take any zero, here zero is not just one number; it's basically column vector. So that is why I make it bold. And lines map to lines, and parallel lines remain parallel. Ratio are always preserved. So first, this property is quite useful while making any encryption algorithm. We have to basically uh, make sure that our any encryption algorithm perhaps have to have less number of fixed points. So that is why we are basically ultimately go towards affine transformation instead of linear transformation while developing any nonlinear component of block cipher. Here we have come up with the affine transformation. Affine transformation are the generalization of Euclidean transformation and combination of linear transformation and translation. In that transformation, this property is quite useful in cryptographic application. That origin doesn't mm, necessarily map to origin. That basically deny the fixed point, and which is quite useful in the encryption algorithm. So rest properties are the same, but we are mainly play with these properties. This first property. Um, there are some famous block ciphers uh, like DES, data encryption algorithm, and AES. Basically, there are number of block cipher, but we basically focus on these two, which are quite famous. And these are all based on SP network substitution and permutation. And this DES is also based on Fistel cipher. And that's fixed confusion component is used, and AES there may be variable component confusion component basically uses mm, two confusion components. One at the sending end and its inverse is at the receiving end. Whereas in AES, the sending and receiving end, they use the same substitution box, and that is as one of the thread to DES analysis. So AES is fundamentally has three versions. One is 128 bits, second one is 192, and third one 256. In AES, basically, we have used a fine transformation to construct our nonlinear component, and it has basically four basic transformation. One is sub-byte transformation, shift row, mix column, and add round key. Today, in the era of research, in the era of advanced communication, and where the things are evolve tremendous in a tremendous way. So the 128 bits and 192 bits and 250 bits it's not may not be enough in the era of quantum uh, communication or quantum computing. But here, if we are talking about the key length of DS64, then there will be a 2 raised to power 64 possibilities to attack, to retrieve your encryption key in case of DS. But in case of AES, we have to apply 2 raised power 128 in case of 128 key length and 2 raised power 192 and 2 raised power 256. In that case, the brute force attack is even impossible for traditional computing capability. But in case of DS, it may be possible that existing computational complexity can achieve 2 power 64 possibilities. It can generate 2 power 64 possibilities while applying brute force attack. So, dear student, I hope you are enjoying, and in next class, in next session, we will discuss some introductory lecture about modern block ciphers, which is DS and AES. Um, for to end up with, we have start with Hill cipher and with famous block ciphers, because in every block cipher there are some linear component as well as non-linear component. So the linear component is also important, and non-linear component is also important. So in late 40s or the late 50s, um, uh, their encryption algorithm are basically utilized in individual ways. That is, they are not using substitution and permutation in a combined way. But right now, after the theory of Claude Shannon in 1949, or after one of his very famous article, which is based on secrecy in information theory, that basically explain how one can make a block cipher a good block cipher. It says that you can not construct a very effective encryption algorithm by just using confusion throughout your encryption algorithm, or just using diffusion throughout your encryption algorithm. So your good block cipher or good encryption algorithm is the combination of both confusion as well as diffusion. And by the way, how we can perform confusion? We can perform confusion with the help of nonlinear component. We call it substitution boxes. And for diffusion, we have performed permutations, as we have take permutation and developing Hill cipher based on permutation. So same is the case while we are in DS and AES, we are also have some substitution as well as permutation steps. So in AES, we have one sub-byte transformation that is correspond to substitution boxes, and shift row mixed column. These are related with permutation component, and we call them as a diffusion component, and sub-byte transformation. We call it as a uh, uh, sub, diffusion component. So sub-byte sorry, I'm really sorry for that. Sub-byte transformation, we call it as a confusion component. So in next lecture, we will be able to develop all these the basics of these two very famous encryption algorithm, which is again fall into the category of block cipher, and blocks are the class of symmetric key encryption algorithm. And symmetric key encryption algorithm, we have only one key, and that one key, through one key who can generate various key for each round. If you have any questions regarding this today lecture, do inform me on our WhatsApp group. I will inshallah respond you. Uh, at last, in that scenario, I must say you have to stay at home and be safe. And may Allah bless you all. Allah Hafiz.